Okay, this is the really the last video of this semester. This is the review of the final exam. Um, okay, so there were two questions in the final, and as you may realize, the first question was just a free question, pretty easy, and I just wanted you to review the general two main estimation methods. So it was, I hope it was a last chance to write down the general principle of the estimators. So, and I just want you to show that they are actually different approach. The least squares, ordinary least squares, and the general method moments are different. They are based on different criteria, but in the end they are the same. But if you see why they are different, then that's enough. That's what I wanted to show you. Simply speaking, you can think the GMM utilizes the first order condition of the least squares. So like a difference between M estimator and Z estimator, one is simply using the first order condition of the M estimator. Anyhow, so they are the same. I believe it was trivial. Now the main problem was question 2. In this question, I wanted to show you, so like the model I give you is the Keynesian model. It is pretty simple, and one of the most important models in macroeconomics. It has a long tradition, so it is pretty simple, easy to see what's going on. But I wanted to show you, actually, it is not that easy to estimate, to handle the endogeneity generated by the simple Keynesian model. But in the end, after watching this review video, you are going to realize, actually, it was not that difficult. Maybe in your answer, when you try the final exam, you must have realized, oh, it was actually not easy to estimate this simple model. But I hope you realize it is not that difficult if you understand how to simplify the problem and how to handle some issues. I'm going to show you different approaches and several tricks. Like seemingly complicated model was actually not that difficult to handle. Okay. So in this Keynesian model, I assume there is only one exogenous variable, investment. I is exogenous, it was a random shock, but endogenous model is consumption, net export, and total outcome, Y, right? So given your income, you decide how much you consume and how much you import or export. And also at the same time, the consumption and export are part of the income. So the third equation is the accounting identity. I don't remember if the name is correct. Anyhow, it is identity. Income equals, like output equals total consumption, right? So, and there are four unknown parameters, alpha, beta, gamma, delta. So the identity is known. Its coefficients are all 1. Coefficients are known, and there is no error term. But even if you have error term here, third error term does not make the problem any more difficult. So let me start. By the way, there are 3 different approaches in this question. First, and in most textbooks, the simultaneous equations model start with a reduced form approach, converting the structural form equations into reduced form equations and then blah blah blah. I'm going to show that, and most of you have done this way, but my conclusion is, my recommendation is not doing that. This is helpful to understand what's going on, and it definitely has some intuition behind it, but it is not practical. It is not that helpful. You are going to see why. And the second approach is the IV regression based approach. So you may interpret each equation as as a regression with endogenous variable. Then its solution is to find an IV instrument variable. So that is the second approach. And it is helpful because you know how to handle instrument, right? So it's better. But the most general and most comprehensive approach is the GMM method, especially when the problem is as simple as this. So the GMM is general enough and easy enough to handle in this case. Okay, let me show you. I'm going to do question A, B, C, D with same questions with 3 different approaches. Of course, they involve a lot of algebra, but in the end, the solution is the same and they're simple. Okay. So the worst approach, reduced form. So we have 3 endogenous variables and 1 exogenous variable. So you have to have 3 equations for 3 endogenous variables. I found that many of you did not write the third equation. That is okay. This is I will explain that later. But in general, this is the most general approach. You have to have 3 equations. And like this is easy algebra in this exam. You can find like pi, lambda, mu can be written in this way. So the left hand side are reduced form parameters and the right hand side are structural form parameters. My algebra may be wrong, but I believe it's correct. And also mu1, mu2. So this is the reduced form approach. So what we can see here is so first we check order condition. That is to compare the number of unknown parameters and the number of available informations. Here we have 4 unknown parameters, alpha, beta, gamma, delta, but 6 reduced form parameters. So we have more information than we need. That means this is why you can ignore mu1 and mu2. That is okay. Still, you have 4 informations for 4 unknown parameters. Actually, the hidden relationship between mu and pi lambda is this. mu1 can be written in this way, and mu2 can be written in this way, right? So then, what's the difference? In theory, analytic solution does not cause any difference because you know the relationship. But in finite sample, if there was an error term in this equality, if there was a third error term in here, then ignoring y will lose some efficiency because different equations contain different weighted error terms. So then the most efficient way is to optimally weight those different informations. That is the intuition. So if you had additional error term, then you have to correctly weight them. However, in this case, we do not allow error term here. So error term does not appear here. Then the intuition goes like this. Alpha and beta depends basically only on epsilon 1, and gamma delta depends only basically, like roughly speaking, epsilon 2 and epsilon 1 are the only parameters. If you ignore the intercept because you can simply demean the intercept, that means only one parameter for one unobserved and unobserved variable, and like it's kind of one-to-one. So you don't need to wait. So you don't need to think about mu1 and mu2. But as I said, if there was epsilon 3, then using mu1 and mu2 and optimally weight all the reduced form parameters will help you. That will improve the efficiency, right? So that's the intuition. But anyhow, reduced form approach is not recommended because I don't know what is the optimally weighted matrix. So optimal weighting is like another problem, so it is not recommended. That's the conclusion. Anyhow, so then after this algebra was crazy, dirty. So this algebra is super complicated, I mean super tedious, annoying, then you will get this. So I could write alpha with two different expressions. The first expression ignores mu, right? So, or in the second expression, I ignore lambda. So you can think it as three sets of equations: pi equation, lambda equation, mu equation, or 1, 2, 3, three equations. As I said, you only need two of them, right? In this case, you only need two of them. If you use the first two equations, you are going to get this guy. But if you ignore the second equation and use the first and third, then you are going to get this equation, this result for alpha. So it's your choice. But as I said, this is suboptimal. This will be inefficient weighting. What I did was just simply putting zero weight on one of the three equations, which is not optimal, but I just wanted to show you this is how the algebra goes. Anyhow, pretty annoying algebra, this step. Most of you have done this part well, but already if you did this algebra, that is suboptimal. You are doing inefficient approach, right? So identification. So based on this like algebra, we can think about identification. First, to identify the reduced form equations, they are regressions. Basically, the reduced form equations are the classical linear regression equations. So we have to check the assumptions, exogeneity and full rank, blah, like this. And we assume exogeneity for investment, and also we assume the full rank, variance of investment should be non-zero, right? And also, additionally, this is for identification of the reduced form equations. Plus, we have to ensure that the reduced form parameters can be converted back to the structural form parameters. To do that, we have to assume this. Beta 0 plus delta 0 should be different from 1, so that the denominator is non-zero, right? So, right? So this is how we guarantee the identification of the structural form parameters. Okay. And then how do we estimate that? Beta hat. So I'm going to use so ignore alpha and gamma. They are intercepts, but more complicated. So let me consider beta only. Delta can go in the same way. Beta can be written as like this. Of course, I'm going to take the simplest formula, right? So again, another problem here. Many of you have difficulty in doing this because you ignored this equation. Because you ignore the third equation, actually that causes the algebra to be more complicated. So if you used third equation, then you are going to simplify beta like this. So then indirect least squares estimator is given this way. And then, even though it looks complicated, but basically it's the OLS. Okay, OLS. And then beta is the ratio between them. The denominators cancel out, and then you get this. And what you can realize is this is the IV regression estimator, an estimator for the IV regression method, regression model. So you can think it as regression of consumption on endogenous variable y and using investment as an instrument. Okay? So after very annoying algebra, the result is pretty simple, right? Which is good. In the end, it's good, but it tells you that this approach is not helpful, not an efficient way. Okay, so let me conclude. There is no general asymptotics, a typo, asymptotic formula for this approach. So the conversion to convert structural parameters to reduce form and then back to the structural parameter, there is no general form. It is not linear, and but in this case, we are fortunate to have a closed form solution, and that was GMM or two-stage least squares estimator. So we can use our knowledge about this estimator. IV regression estimator can help us derive the asymptotics, right? You can use the existing knowledge. So this is the conclusion. I don't recommend this approach. You did this approach. I taught it because it contains intuition. And this is the textbook method, right? I have to teach what textbooks teach. So that's why I taught it. But don't use it in practice. This is not what you do in practice. And it will make yourself in a tough situation. There is no unified general asymptotic result. There is no algebra unified or like general algebra for this. So you see. Okay, so then the second approach is the IV regression approach. Now I will take only one equation, structural form equation like this. This is the first equation, and clearly y is endogenous. So if epsilon 1 increases, that will increase C, and then higher consumption means higher output, and higher output will increase the consumption again. So that's the endogeneity. So I'm going to use the investment as an instrument, right? We have to check then two assumptions for identification of beta. To use for an instrument, we need to check relevance and independence. Relevance assumption, covariance non-zero. This is guaranteed by the accounting identity. By the way, I forgot to mention this. Accounting identity, in the accounting identity for this to be non-zero, actually we need this assumption. I forgot to say this, right? I had to show you this assumption is required for the relevance assumption, right? So you can calculate the covariance between I and y. That means mu2 is non-zero. For mu2 to be non-zero, the denominator should be non-zero, right? So that is the covariance. So I missed that condition here. But independence assumption is satisfied by the assumption given in the question. So alpha and beta are identified by the result we learned in chapter 1 or chapter 2, excuse me. Okay, so it is one endogeneity regression model with IV. Identification was good, and then we learned how to calculate the estimator using the instrument. You may use the GMM or the two-stage least squares. It was a simple case with one-dimensional endogenous variable, one-dimensional instrument, so it's trivial. We learned the result takes this form. Okay, this was the result, and then under the homoscedasticity assumption, for simplicity, we can show that the asymptotic variance is given by this form. This was the result we learned in chapter 4. So, by the way, this estimator is the same estimator as the reduced form approach. The estimator from the reduced form approach. So, the asymptotic variance from the reduced form approach should be the same, like this. Okay? So, we are using the result from the GMM and two-stage least squares. Similarly, you can do the same thing for delta. And asymptotic variance of delta is given this way. Okay? So, as you can see, now you see the difference, how stupid it was to use the reduced form approach. Reduced form is you are actually making everything more complicated, right? Not using the existing clean result. But the problem with the IV regression approach is that you cannot tell the covariance because we are looking at equation by equation. Here, I'm only considering the first equation only. And separately, I consider the second equation to identify delta. That is not a problem if you are only interested in beta and delta. But in the end, we would like to test whether beta and delta are the same or not. That means we need to estimate the covariance. We need to consider the covariance between two different equations, but we consider them separately. So that's the limitation. So that's why we call this limited information approach. Then I will show you how to do that. So to do that, we are going to use the influence function of each estimator. Okay. To brief review of the influence function method, we are going to show that we would like to assume that beta hat minus beta 0, the estimation error in beta hat, takes this form, some average of something plus small op, ignorable term. And similarly, there is another influence function di for delta. By the way, in the question, the subscript was t, but here I'm using I. It was my mistake. Notation inconsistency. I'm sorry about that, but doesn't matter. You can replace I with t. So, and additionally, we have to know that the mean should be 0, so that the estimator is unbiased. Okay, asymptotically unbiased. And then, if you know these two results, influence functions, then by the central limit theorem, after multiplying square root n, it converges to a normal distribution in distribution. Normal distribution with mean 0 because the mean is 0, and the variance is the variance of these influence functions. And multiplying square root n, these ignorable residuals will go to 0 even after multiplying square root n. So square root n will be cancelled out, and still it's small op1. Okay, this was brief review. Anyhow, the covariance between beta and delta is this part, this guy. This is the covariance between the two estimators, right? So even though we calculate them separately, identify them separately, we could calculate the covariance using this technique. And I'm going to show that then what remains is we have to find out the influence function. What is this B and D? I will show that this is the influence function. I realized notation is inconsistent here. BT should be BT, but please understand. And to do that, standard technique, C is replaced with the equation, and then you can write beta hat as... by the way, I'm going to assume that there is no intercept, mean 0. Everything is mean 0. Demean all the variables. For simplicity of the algebra, then you can simplify the formula this way because the average is 0. We know the average is 0. And then beta 0 plus epsilon. We are going to reveal epsilon in this technique. And then what is the main randomness is epsilon. The problem is in the denominator. So denominator has another randomness because it's finite sample. But we are going to ignore them for now in the influence function. Influence function has only one randomness in epsilon. Denominator is a constant expected value. But its difference between this denominator and this denominator is taken care by the residual. The residual includes that difference, and it is ignorable. We are going to show that this is ignorable. Okay, so now look at this. Beta hat minus beta 0 is an average of something, in average of influence function plus this much residual. And we know that it's easy to show that this influence function is mean 0. Then what we need to show is the residual is ignorable, small enough, converging to 0, fast enough. To show that, we are going to show this, which means if you multiply, even if you multiply square root n on the left hand side, it should go to 0. Converge in probability to 0 after multiplying square root n, which is also easy to show that. Square root n is multiplied to the first term, which is normal distribution, like which limiting distribution is normal distribution. So it is big OP1, which means it is bounded in probability. It does not diverge to infinity. It's nicely distributed, has a nice limiting distribution. And the other second term, the second term is small OP1. It converges to 0 by the weak law of large number. So this converges to 0, and continuous mapping theorem and weak law of large number shows that this converges to 0. So that means after multiplying square root n, the first term does not diverge. It does not go to infinity. But the second term goes to 0. So if you multiply them, the total, the whole term will converge to 0. Okay? So proof is complete. And that means we have influence functions satisfying our conditions. Then under the homoscedasticity, you can calculate their covariance. So remember, go back to here. What we need is the covariance between two influence functions. That is the asymptotic covariance of these two estimators. It is not that difficult. You can, calculate the covariance this way, and that is like this, right? And now you may think about this, like this covariance is very similar to the asymptotic variance of a single estimator. A single estimator has the same component with covariance replaced with variance. Okay, so from this comparison, I'm sure that I'm right, right? It should be correct, I guess. Okay. So this is the IV regression approach. As you can see, we are using one equation only. We are considering equation by equation. So if you are interested only in the only in one equation, then this is very helpful. And or if the model is too complicated to consider everything at the same time, then separating out one equation will help you, like this, right? If there are like say 100 equations, then you cannot handle them at the same time. Then just taking one equation and estimate only one equation will help you. However, it is not general enough to study across equations. So that is clear limitation of this approach. So I'm telling you, it's not general enough. So it may be inconvenient depending on what you want to study. Okay. The third approach is the GMM approach, and it will consider everything at the same time as a moment condition. So we have 4 exogenate assumptions. Of course, we have mean zero. Those two mean zero assumptions are needed to identify the intercepts and exogeneity for the instrument. So 4 assumptions for 4 parameters, alpha, beta, gamma, delta. And moment functions can be written in this way. Okay, right? So what's nice about this is everything is linear. The moment conditions are linear. So even though it looked quite complicated, but actually it is not that complicated. So you may write the moment function this way. Intercept part, so G, the moment function is something minus something times theta. So something takes this form. Especially this part is block diagonal. The block diagonal terms are 0. Off diagonal terms are 0. So it will be easy to handle. So then, and furthermore, it is easy because there is no weighting matrix. You don't need a weighting matrix because you have 4 parameters for 4 moment conditions. So no weighting matrix needed. Therefore, the sample GMM criterion function takes this form. A bar is, of course, sample average of this AT. Sample average of A, sample average of B, and quadratic, no weighting matrix, or the weighting matrix equals identity, then you get this. And then it is a quadratic form. If you expand this guy, you can write it this way. I don't need the constant because remember, it's a quadratic function. To minimize it, the constant does not matter. So plus constant does not change the minimization. So based on this quadratic part, you can minimize this using this formula, right? When I was in high school, the quadratic function minimum, I remember I memorized the quadratic function's extreme value is minus b over 2a, right? So using that, a was the coefficient of x squared, b was coefficient of x. So you get this. You can do the first of the condition and you can do that kind of things. Maybe b prime transpose maybe here. I'm not certain. Anyhow, I need to check it. Transpose here. I forgot transposing a and another transpose here. Okay, sorry about that. And still, this inversion is quite complicated. So we are going to remove demean the variables again. So I'm going to remove the intercepts, and I will use only two exogenated conditions, and then those matrices will be very simple. Especially B becomes pretty simple. The same thing in the diagonal terms and 0 of diagonal terms. So easy to calculate them. Another transpose missing here. So in the end, if you do the algebra, I didn't do it, but if you do the algebra, you should get the same same estimator like this. This is the answer, right? Of course, in that case, the demean part is this part, average part is 0, so should be the same. In the end, everything will be the same as the IV regression approach because everything is linear, everything is simple, so there is no difference whatever you use. And the asymptotic variance is known as this guy. Again, you can use the general formula, and we know the specific components. Omega takes this form, by the way. So this is variance of epsilon 1. This is covariance between epsilon 1 and 2, variance of epsilon 2. So anyhow, you can ignore the weighting matrix, and G is simple because the moment function was linear. And if you do math, possibly more complicated, but still you can get it. It is like 2x2 algebra, possibly annoying. But what's nice about this is general. You are just following the formula. So you just follow the formula, check the assumptions for the formula, then you will get the covariance. In the end, no matter what you use, you are going to get this as a result, and you are going to get this as the asymptotic variance matrix of beta hat and delta hat. So the covariance is obtained here. So as I said, the GMM matrix is general, and the IV regression approach is more, specific to several equations. But in any case, the reduced form approach is not efficient. It's not a clever idea to do that. Once you get the asymptotic formula, asymptotic distribution, then you know how to calculate the variance. Calculate the variance of investment, covariance between them, and the variances are based on epsilon hat like this. So there is no problem in our calculation, right? Standard method. And then now, if you take the asymptotic matrix as M, say M is the asymptotic matrix, variance matrix of this guy, then the wild test statistic will take this form. Because everything is scalar, I do not use transpose, M inverse transpose, M inverse and something. So I just use it as a scalar. And we know it converges to chi-square 1. under the null hypothesis. So the null limiting distribution is chi-square 1. And then what remains is to calculate m. How do we find the asymptotic variance of beta minus delta? It is just a linear function of the vector, right? Multiplying this vector is just this one, and then the asymptotic variance can be calculated using the same, but by multiplying the same vector in front and in post multiply and pre multiply, post multiply. Typo. There shouldn't be any transpose here. Transpose is here. So you have to delete transpose here. Excuse me. And then, you can calculate this, and you know how to test it. So as you can see, if you take step by step, it is pretty standard. And we considered very simple model, but it can be very complicated. But as I said, if you don't get confused, just follow the basic principles. Then you will get the answer. Okay, if you have any more questions, I would be happy to help you. So again, good luck with your prelims, and hope you survive. Okay, see you later. Bye.